The development of LNG projects involving ocean transportation of LNG has meant the construction and operation of a new and highly specialized type of vessel, the LNG carrier. The particular characteristics of an LNG cargo require special attention to be given to cargo handling instructions. This has led Shell to carry out a series of controlled tests on jettisoning LNG at sea to ensure that, should this ever be necessary, the procedures recommended were practicable and safe. When spilt onto water, LNG spreads across the surface and at the same time rapidly evaporates to form a dense vapor. As jettisoning proceeds, it's important for ship safety that the LNG layer on the water surface does not contact the ship's hull, and the vapor cloud produced remains clear of potential shipboard ignition sources. The 75,000 cubic meter vessel Gadilla, one of the 7 LNG carriers built for the Brunei-Japan project, was used for the tests. These were carried out with the carrier both steaming ahead and stationary. LNG from one of the ship's tanks was pumped via the cargo lines to the discharge nozzle fitted at the stern of all Shell's LNG carriers. A series of 6 tests were carried out, with the carrier both steaming ahead and stationary. 2 different nozzle sizes and corresponding LNG discharge rates were used. In both cases, a discharge was made with the carrier stationary to simulate the most severe case for jettisoning cargo, should this ever be necessary. Of these tests, numbers 4 and 6 are of prime interest and will now be examined in more detail. In test number 4, 1 cargo pump was used to discharge 76 cubic meters of LNG in 10 minutes. The discharge rate and nozzle diameter of 51 millimeters employed in the first series of tests were less than those proposed for actual jettison operations, so that the feasibility and safety of the system could be established before the full-scale jettisoning exercise. As can be seen, the jet of LNG fell well clear of the stern of the stationary ship. Even with the light wind, varying between 5 and 12 knots, blowing from 24 degrees off the bow, the vapor cloud never approached the stern, the closest distance being of the order of 60 to 70 meters. The trajectory of the jet to the point of impact with the sea was close to that predicted by theory. Cold LNG vapor is appreciably denser than ambient air and tends to form a flat cloud, which characteristically hugs the water surface for some distance downwind. When viewed from the ship's stern, this behavior is immediately apparent, as the clearly visible flat white cloud rolls over the water downwind of the ship, with little tendency to rise appreciably above the sea surface. The high velocity of the LNG at the discharge nozzle produced a highly turbulent jet in which entrained air evaporated the bulk of the liquid before landing on the sea. No pools of LNG were detected by the airborne infrared cameras. Towards the end of the 10-minute discharge, a large plume had been established, which under the light wind conditions extended no more than 1,400 meters downwind with a maximum width of 300 meters. With stronger winds, the plume would have been significantly smaller. The reluctance of the vapor to rise and disperse was reflected in the height of this plume, which never exceeded between 8 and 10 meters. After completion of the discharge, the vapor cloud dispersed completely in approximately 10 minutes. For test 6, the final test with the carrier stationary, both the flow rate and the discharge nozzle diameter were increased to those intended in an actual situation. With 2 cargo pumps in operation, 193 cubic meters of LNG were discharged in 10 minutes through a nozzle of 102 millimeters in diameter. Similar results to test 4 were obtained. The discharge jet landed well clear of the ship's stern, and the vapor spread downwind from the point of impact to form the familiar shallow cloud. This can be clearly seen from the aerial view. During all these tests, a field meter was used to measure the electrostatic field strength around the discharge jet and nozzle. The low values observed present no hazard to the safety of the operation. The visible cloud following an LNG spill on water is the result of condensation of water vapor from the atmosphere to form a fog, as warm, moist air mixes with the intensely cold LNG vapor. From the temperature and humidity at the test site, dew point calculations show that the visible cloud should disappear at a gas concentration of about 0.5% of methane, which is considerably less than the lower flammable limit of 5% methane in air. Consequently, the flammable region is well within the visible cloud, and this will apply to all LNG spills on water. In this final test, the visible plume extended 2,250 meters downwind, and even over this distance did not rise to more than 10 to 12 meters in height. After completion of this full-scale test, the vapor cloud dispersed completely in 15 to 20 minutes. Even if a complete tank were to be discharged at this rate, the visible plume size and dispersal rate would be very similar. Results of these tests have been used to predict the dispersion of the LNG vapor cloud produced. An analysis of observed plume dimensions led to empirical values of the dispersion coefficients for LNG plumes. Using these, the predicted 0.5% methane contour, shown as a dashed white line, correlates well with the somewhat ragged outline of the visible cloud formed in test 6, which was calculated to disappear at a gas concentration of about 0.5% methane. Assuming a 2-to-1 peak-to-average concentration ratio, an important prediction from these tests is that the hazardous zone from this cloud would only cover the much smaller area shown by the red line, less than 1/3 of the length of the visible cloud. These tests have shown that LNG may be safely jettisoned at sea from the stern, provided adequate safety precautions are taken. As a result, operating instructions have been established and issued to the masters of our LNG carriers for the safe jettisoning of cargo.